In an engine running in accord with the Carnot cycle, 100 joules of energy is withdrawn from the hot source at 500 Kelvin and some is used to do work, with the remainder deposited in the cold sink at 300 Kelvin. How much energy was used to do work? So we can use the formula QH, so the heat of the hot source, divided by QC, so the heat that's been deposited on the cold sink, equals minus TH, so the temperature of the hot source in Kelvin, divided by TC, the temperature of the cold sink. Now, our hot source is losing 100 joules of energy. So QH is going to equal minus 100 divided by QC, so that's the heat or the energy that's being deposited onto the cold sink, and that's equal to minus 500 divided by 300. And we can solve for QC, and QC is equal to 60 joules. This is the amount of energy or heat that's being deposited onto the cold sink. Now, this machine or whatever this engine is doing, it wants to do work. So the energy or the heat that's being deposited onto the cold sink is being wasted. So how much is then being used to do work? So remember, we're starting off with 100. 60 is being used in the cold sink. So that's wasted essentially. That means the 40 must be used to be doing work. Now, of course, there is another way that we can solve this, is we can use the efficiency formula. And the efficiency formula is, so the efficiency of an engine is equal to 1 minus TC divided by TH. So that's equal to 1 minus 300 divided by 500, which is equal to 0.4, or we can say 40% efficient. So the amount that's doing work is going to be 100 multiplied by 0.4, which is 40 joules. Now let's take a look at the next one. How much work can be extracted when the temperature of the hot source is increased to 800 Kelvin? So this is related to the question we've just done. So again, we can use the first formula. So QH divided by QC is equal to minus TH divided by TC. So QH is still going to be minus 100. We're still removing 100 joules of energy from the hot source, divided by QC. That's equal to minus 800. So the hot source now has 800 Kelvin temperature, divided by, and the cold sink is still 300. Now you can solve for QC, and QC is going to equal 37.5 joules. So what this says is, by increasing the temperature of the hot source, we are essentially reducing the amount of waste or wasted energy that's being deposited on the cold sink. So from that 100, 37.5 is going into the cold sink. And that means 62.5 is going to do work. Again, we can use the efficiency formula to calculate this. So the efficiency is going to equal 1 minus TC divided by TH. That's equal to 1 minus 300 divided by 800. And that's equal to 0.625 or 62.5% efficient. So to work out the amount of work done, it's going to be 100 multiplied by 0.625, which is 62.5 joules of work. You get the same answer. Now let's take a look at another problem. And the problem reads, a certain power station operates with superheated steam at 573 Kelvin and discharges the waste heat into the environment at 293 Kelvin. The theoretical efficiency is therefore 48.9%. What temperature of the hot source would the theoretical efficiency reach 80%? So here what we want to do is we want to solve for the percentage. So 80% is 0.8. So efficiency is equal to 1 minus temperature of the cold divided by temperature of the hot. So 0.8 is going to equal 1 minus, well, the temperature of the cold sink or the environment is 293 divided by TH. And now we can solve for TH. So TH is equal to 1465 Kelvin. So in other words, if you increase the temperature from 573 Kelvin to 1465 Kelvin, you are increasing the theoretical efficiency from 48.9% to 80%.